BBSR seminar. Today we have Kathleen Torkko. She'll be giving a talk about survival analysis. So Kathleen is in the Department of Pathology and Biostatistics and Informatics. And she's also part of the BBSR. So Kathleen, do you want to get started?
Cool. Yeah, I'm kind of a hybrid person straddling pathology and biostatistics, but my education is in epidemiology and public health. But I do a lot of statistics and work a lot with basic scientists. So today, I think it was requested that we cover survival analysis in this seminar. And so today I'm going to actually give a little talk and a practicum about doing at least a Kaplan-Meier analysis in prism. Let me see if I can share. Let's see, let me share the screen. DDD. Let's see, can you see the lecture notes? Now what happens if I go to full share? Is that going to?
Yeah, right now we see the entire app.
Yeah. So let me go to the slideshow. Okay, so tell me what you see. You just see the first slide?
Just the slide.
Okay, perfect. Okay, so today it will be a discussion survival analyses, at least as it pertains to the Kaplan-Meier curve and log rank test as shown in this first graph. Today's objectives, I want to focus on have fun, because I do think that survival analysis is one of the elegant analyses you can do, very intuitive and easy. It's kind of like the ANOVA analysis in the lecture I gave last year. But we're going to talk about the important aspects of a survival analysis as it relates to Kaplan-Meier in terms of how censoring is used and the importance of time, including time in the model. And then we'll go over practical examples of using data from a couple recent Nature papers and go over how to do that analysis in prism. And unfortunately, I don't have time to talk except in passing about probably another very important survival procedure in terms of the Cox proportional hazards model, which would be a good topic for a future lecture. So this first figure I had on the first slide is actually from a paper last year where they were looking at radiation treatment in conjunction with breast cancer receptor status, which they broke down in this first graph to, of course, hormone receptor positive or negative and HER2/neu receptor positive or negative. And those of us, intuitively, you just look at this graph and you say, I don't want to be the red line. Obviously, these are the people who have the poor survival in this graph. And this is actually the triple negative breast cancer group. So what a survival analysis, a classical analysis, is looking at survival. And I think there's a reason why it was called survival analysis based on the bias that we kind of have in wanting to understand what kills us, what causes us to move on to another plane. And this is certainly from the mid-1600s when a man named John Grant was publishing his bills of mortality about the leading causes of death in London and surrounds during that time. And he also was first to use a kind of a life table method. So it started early on in us wanting to understand how we die and when. And I think that carried over to how we name, and originally we're using these survival analyses. But as we'll see, you can use it to model many things other than just survival. But here classically, they start at 100%, everybody's alive. And then over time, as you follow, that people will then tend to have the event in this model, which is death from breast cancer. It's a breast cancer specific model rather than overall death model. So all these people in each little step in the model represents at least one or two events of people who have met that event and have died. Now this, if you don't look at the y-axis, which indicates present survival, you might think that most people are dying, but I want to point out that this is actually a truncated axis, which I have a little bit of issue with. I think it probably should run the whole range from 0 to 100, but the authors probably did this to just show that they're to illustrate the difference better between the four groups. They also include a p-value, which is not anywhere indicated in the figure legend or on the figure what it is, but from the text you could found out it was a log rank test. So p less than 0.001, if you had your significance level set at 0.05, you would conclude that there's statistical evidence that there is a difference between these four groups, or these, at least one of these groups from the other. This is a nice illustration, but it doesn't include, I think if you're going to do a survival plot like this, include sample size somewhere in the figure, on the figure or in the legend, so you have an idea about the numbers in the graph. That's important. And also indicate what your p-value is measuring. Another example of a survival curve is starting also at 100%, and it's modeling death from, oh, no, sorry. It's no deterioration in quality of life. So this is looking at people who, I guess, start with very good quality of life, but as they proceed on these treatments, so once they start taking either the, I'm not good to pronounce it, I'll call it the AB drug, but this is one of those fancy new PD-1 or PDL1 immunotherapies compared to the sorafenib. And right away, you tell that sorafenib is actually worse in terms of determining quality of life. There's more deterioration from the start of taking the drug on over time. And this is up to just over 2 years. I like this graph in terms of the fact that it gives you sample size. It gives you some indication. It tells you some data about the graph. And this is the median time to quality of life deterioration, which is taken from here, the 50%. If you're a glass half full, you might say 50% still have good quality of life. Or if you're glass half empty, you might say 50% have a deteriorating quality of life. But you take it, you go across here, and you about here, you'll drop down. And you see this is about 3.5. They calculate 3.6 months for median survival in the sorafenib. In the AB group, it actually works out, it almost doesn't cross the 50%. But here at 11.2 months, it does. So you see that people on the AB have better quality of life for a longer period of time. And they also include, they don't have a p-value in here, but they did calculate a hazard ratio from this, where the 95% confidence intervals do not include 1, which means if you calculated a p-value for this, it would be less than the 0.05 if that's your cutoff for significance. And a hazard ratio of 0.63, they would be modeling here the AB group to the sorafenib, saying that actually the AB group was at reduced risk, about 40% reduced risk for overall maintaining quality of life. Now we have another one. This is not a cancer example, but I thought I'd use a few COVID examples in the lecture to be a little timely. This is from a recent paper in Nature where they were looking at ways to get people to get their first COVID vaccination. And this was in a large health center, I guess, in Southern California. And for a part of the group, they gave them a nudge, which is a kind of a behavioral thing. They sent them a text message and reminded them to get their COVID vaccination. So the event in this thing is they're studying when they get their COVID vaccination. And the people at the nudge, represented by this brown or red line, are people who they got it a little bit earlier, and by the end of the follow-up period, they're about 4 percentage points more, 4% more people got it compared to those who didn't get the nudge. So survival analyses can be used to model all sorts of things and all sorts of outcomes. But the main thing that binds all these together is you're looking at time to something happening, time to when you get your first COVID shot, time to when you die from breast cancer after you get diagnosed with breast cancer. So you want to know not just if it happened, but when it happened and how soon did it happen and what time. So time is a very important part in the model. It's not only just the time that it takes for somebody to develop the event, but it's also observation time that it takes, that you observe people while waiting to see if they develop some kind of an event. Also, if they didn't develop the event. And events can be anything. It could be death, it can be recovery, it can be remission. You can have all positive or negative. It's not all about death. So you can really model a whole bunch of things as long as you have time to event data. And the data that we're studying, we're following people over time, which makes this a longitudinal study or prospective study, which has its own methodological problems. Here's an example. This is from a British publication. That's why the date formats are a little bit different from ours, but they were looking at renal replacement therapy for people who go into kidney failure. And this is it's related to having, I'm not quite sure the exact type of treatment it is, but what they did was they wanted to map and find out what the time of death is after they started on this therapy. So they started with a very defined observation period or study period of 10 years from the 1st of January 96 until the end of 2005. With this line in the middle was where they stopped their accrual into the study because they wanted to allow people time to experience the event, to give time to develop it after they start treatment. So what they have here then, so you've got the defined period, and then you have time where people are being studied in the model, where you have this person here started their renal replacement therapy on this date, and they were followed about 6 months until this date, where fortunately they recovered their renal function and they were taken off the therapy. This person started their renal replacement therapy on this specific date and was followed probably about 7 years until we reached this wall of the end of the study. And they didn't die, which is fortunate, but we don't know exactly what happened to them other than they didn't die over this period. This person had started their replacement therapy on this date, was followed probably for another 7 years, and died on this specific date. And we had 5 deaths overall in this cohort, but here's another person here who started their therapy here, was followed about 5 years, and then was lost to follow-up. What did they move to Milwaukee? Or I guess this is England, maybe they moved to Edinburgh and out of the study area, but something happened where you don't know. They didn't die in the period, but they were lost to follow-up. And this is something that is inevitable if you're going to do any kind of longitudinal or clinical trial, is that people are going to be lost. And it's just part of doing the study, and you'll plan your sample size with the idea that we've got to pad the sample size a little bit because we're sure that we are going to lose some people. They're not going to follow the whole time. So attrition is really a serious methodological issue. But also we have to worry about our people who drop out are different from those who stayed in. And this is something you worry about in a survival analysis, like is there risk for experiencing the event the same or different from those? And we'll talk a little bit more about that. But censoring then is an important concept and feature of survival analyses that deals with this problem of attrition, where you have people who have are followed, like that person was followed for 5 years in the renal replacement therapy, and you observe that person for 5 years, and maybe you took measurements every 6 months or so, drew blood or measured kidney function in some way over that period, so that all that information potentially lost because you don't know if this person actually died, but you know they didn't die during the period that you observed them. Well, people who are either lost to follow-up or reach the end of the study period and don't have your event, these people are considered censored. And the information that they provide in the time that you observed them, even if it was like the 6 months for that one who had a recovery from their kidney failure, or the person that was just lost to follow-up, you can use that in the model. And that's where we come to these two very intelligent gentlemen, Edward Kaplan and Paul Meyer, who published a paper in 1958 that proposed and explained this Kaplan-Meyer model. Now, if they'd switch authors, if Meyer had been first author, we'd call it the Meyer-Kaplan. Anyway, that's just a what-if situation. But Kaplan and Meyer came up with a method where you can manage the fact that people have time in a model but don't experience the event, but you can still use that information to study overall risk for disease or for the outcome. And I just include here as an aside that another important development was from David Cox in 1972, who was later knighted for his contributions, but he then published about the Cox proportional hazards model, which is a step up in many ways from the Kaplan-Meyer in that you are able to do a multivariable or multivariate analyses to include other variables that might help refine your risk estimates. So the Kaplan-Meier curves, you're plotting time to event or your time in study if you don't have the event. You usually start with 100%, or you can start with 1 if you're talking about proportions. People, I think, tend to like the 100% because then you can say you 100% of people are surviving. It's a little bit easier to explain. And the y-axis always includes the time where you start from the start of the observation periods, or from when people are first observed, and you follow the time through to the last time period, or the longest time period that people are followed. And so you have 100%, they all don't have whatever event you have. And over time, with each step, 1 or more people are having the event, or mice if you're studying animals. And then you can then look at how you have decreasing survival. And overall, I mean, our own personal survival curves, everybody dies at the end. But so if you follow people long enough, you'll eventually get to 0. But fortunately, that doesn't always happen in terms of the study periods. Okay, requirements for Kaplan-Meier curve. You have to have your time to event data. So you're interested in when the event happens, but you also need a clearly defined observation or study period and a clearly defined event. Like, what exactly do you define as breast cancer specific survival or death? So you would, when you plan your study, you would be sure to state these particular measurements or particular conditions. And also you need to be able to define the time and model for each participant precisely. So know when they developed cancer and know when they had remission. So then you can calculate the time to that event precisely. Also, you need to get to 2 mutually exclusive states in your event, and that are you either censored, so you didn't have the event while you were being observed, or you had the event. And usually when you code this in your data, you would code it as 0 for being censored and 1 for the event. Now you could say 99 was the event and 23 was the censored. You could put whatever value you want here, but I would stick to what is convention and do 0 and 1. So if you ever want to share your data, people are going to have a little bit better understanding of what you did. So to calculate time, it's simple. You just know the dates of when things happened. For people who have the event, you subtract from the date of event, the date of start to follow-up, and you get a number of days, and you can calculate that as number of years or months or whatever it works. And for people who are censored, who don't have the event, you just calculate the date of last follow-up, and that might be the date of the end of study. And then you subtract that from the date of start of follow-up. And so you can then get some very precise estimates. So if we look at this graph where we had the renal replacement therapy, this person 1 started on this state and recovered on this state and ended their therapy. And you would then calculate the number of days, or maybe it works out to be 6 months. And they would, in your data sheet, you'd have patient 1 follow-up time 6 months, and the event code would be 0 because he was censored. Here we have the person who started on this state, calculate, maybe that's 7 years. They would be put 7 years and then censored because they did not have the event. And you would go on down. These people had the event and you put their time, and the loss to follow-up would be maybe 5 years, and would put a 0 as being censored. Now you do have different kinds of censoring. I'm sure you've heard of left and right censoring. And actually the Kaplan-Meier and other survival analyses are designed to deal with right censoring, which is perfectly, I mean, it's not perfectly okay because you don't want to lose information on these people. You have incomplete, but you don't want to lose all the information on the people. So you can categorize them as censored. And it's right censoring because on the timeline, it's happening on the right side of the timeline. And so people who are lost to follow-up or people who don't have the event by end can be censored and can be included in the models. Left censoring is problematic, and usually you are not going to include these in your study. Here's a person, the close care here is a cancer diagnosis followed through time until you get to cancer recurrence. This person had their cancer diagnosis sometime before your observation period, and their cancer occurrence during the observation. Now, if you knew, usually you know when you're diagnosed with cancer, that's a pretty hard date. You understand when that diagnosis came. But there are some events that you might not, or some entry criteria or definitions might not be so precise. So you might be relying on recall for people to decide, well, yeah, I think it was this date. So this time might not be able to be calculated, the follow-up time, very accurately. Plus, if you were measuring things on this during the time you're observing, like every 6 months, maybe you do a blood draw and take blood pressure or whatever measurements you would take, you would be missing that information on this side of the curve. And besides, if you plan the study, I'm sure that your definition of including a person into the study would be they would have a cancer diagnosis, a new cancer diagnosis, and then you would follow. It might be a new cancer diagnosis of a specific stage and grade, but you need to have the event that you're following forward in time to occur within your period of observation. So you do not, unless maybe this is a very, very rare cancer and you try to get as many cases as you can, you know this person was observed, it was diagnosed a month before, a week before, maybe you would include it in that case, but explain that in your methodology. But for the most part, no left censoring is not allowed. But right censoring is why we do a survival analyses. There are assumptions if you're doing survival analysis. One is that your survivor probability should be fairly constant over time. So your observation time, you shouldn't have it that the probability of dying is changing, like maybe there's a new treatment that increases survival, or you get a more virulent disease appearing which decreases survival. So you want to try to, you hope that the survival probabilities for people enrolling in the study is the same for these people as it is for these people. And you can test that by splitting your analysis and looking at people who enrolled early and seeing if you get the same result of those who enroll late. Now, another assumption is the censoring of the people who are lost to follow-up or don't experience the event is non-informative, that it is randomly censored, that you want to assume that the person who is censored has had the same probability of experiencing the outcome as a person who stayed in the study. And there are ways that we can try to assess that, but it's not really as easily tested as splitting the time for looking at risk over time. Now, example of how risk can change, I'm going to go to COVID again. And this is a timeline of some seminal events in COVID history, where it was first discovered in mid-December, first appeared in Wuhan, China, made it to the US by January. And over time, and then by August of 2020, it became the third leading cause of death in the US. But if you're looking at risk to death from COVID, it's probably pretty constant. The risk for getting COVID increases as the number of cases increase, but as it becomes more widespread. But something happened then in mid-December when the FDA gave the emergency use authorization for Pfizer and Moderna, and a couple of months later to Johnson & Johnson. That's going to change the risk probability because people who are vaccinated will have a much reduced risk, or do have a much reduced risk for death from COVID. So you have to, if you be aware of these things, if you want to study the risk for death across this time period, you have to be aware that this is going to be a thing that could change risk over time. And you can handle this by analyzing people who are vaccinated separately from people who are unvaccinated. And then you have another event here where you have a more virulent strain that comes apart, that the Delta strain is now the most predominant one as of last August, that we have to take that into account. So be aware of your disease process and how that could affect your survival probabilities over time. And if you have curves that cross, if you plot your data and you see that your curves cross, you know that you don't have a constant risk over time, especially between the two groups. This is an example where they have bone marrow transplant and they have the autologous, is what you donate your own marrow to yourself, and the donor bone marrow transplant. You see at the beginning, there's a much steeper, much higher risk for death for people who have the donor because of higher chemotherapy and suppression of immune system. But over time, these cells, if they survive, actually do a better job of protecting the host from death, whereas the patient's own, the death from that continues to decrease. So if you find that your curves cross, you know that probably a Kaplan-Meier analysis is not really appropriate for that, because you violate that assumption that you have equal risk across the time period in the groups. Informative versus non-informative, or non-random versus random censoring. Censoring is not a problem. It's just inevitable when you have a prospective study, and the longer you study people, the more likely you're going to have people dropping out. But if they drop out, if it's non-informative, like they move to Milwaukee or they lose interest or they get sick for other things, that's to be expected. That's going to happen. And if it's something that happens equally, if you're comparing two curves, for example, it happens equally across the two curves, the same amount and the same pattern, then that's not going to really bias your estimate of survival and comparing the two curves. But however, if you have dropout, if say you're doing a treatment study looking at some new treatment and placebo, say that people who get the treatment, you enroll people who are sick and they get the treatment, and this thing is such a wonderful drug that people get well early and they drop out because they feel good, or maybe the treatment makes them feel sick, get upset stomach or whatever. They drop out early. And that happens only in the treatment group compared to placebo. This is going to bias your estimate of your survival for between the treatment and placebo, and should be avoided. So here's an example of a curve. This is another COVID one, where a paper from last year, they were looking at differences in survival from COVID-19. So they're looking, actually the event was death from COVID-19 between men and women. And they found that women overall have better survival. And these are in men and women who are matched for potential comorbidities like obesity and heart disease. They found women have a better survival. And this is actually a nice graph because it does give the log rank test. It's a chi-square test. And here's the test statistic, degrees of freedom, and the p-value gives you the numbers of people. Those are the outcome and the survival probability at the end of the follow-up period, which leveled out at 86 for women and 74 for men. But what this shows, the dots, and this is the point of censoring, is they plotted censoring along the line for both. So these are people who were censored over time. And these people, you can see that there seemed to be a similar, it was all across the whole observation period, and seems to be a similar pattern and similar amount between the two groups. So I think this would be a fair example of what I would call random censoring. So to start to build a Kaplan-Meier curve, oh, and by the way, if you have any questions, please unmute and ask me any questions. I'm not following chat, or if somebody is following chat, they can let me know. But to start with the beginning of the Kaplan-Meier curve is here we have our observation period, our data. We've calculated the time of each individual was observed during the observation period, and whether that they met the event or they were censored. Censored being shown by open diamonds and event by close. So what you do is, after you've calculated the time and model and whether they were censored or had the event, you would put them in order from the shortest follow-up to the longest. And this is a graphical distribution. You don't have to do this to do it. You would just calculate the time and put it in your spreadsheet as patient H had a 1-month follow-up and was censored, so you categorize as 0. Patient G had about 1.5 months of follow-up, and well, you know precisely what it was, I'm just guessing, and they had an event, so they're 1. And we eliminated A from the analysis due to less censoring. So you arrange everything in order from shortest follow-up, and then you start calculating your survival curve. And if you did it by hand, what you would do is this is again, going back to the renal replacement therapy study, and this is in 50 patients. And what you do is here are the days from the shortest observation period, and the longest is out here at about 3,500 days, but in this table, they stopped it at about the median survival here at 1,708 days, which is right about here. But they go through, and so starting at the beginning, at the 0 time, the number at risk, that's number of people who have the potential to develop the event, there are 50. There are no deaths, they're all alive, there's 100% survival at the beginning. And that's here at the top left corner of the graph. The first event happened, whether censored or somebody died in this case was at 34 days. So you go, and at the beginning of at that 34 day, there were actually 50 people at risk still. One died, there weren't any censored. So the probability of surviving on this day 34 is 49 out of 50 or 98%. And to calculate the cumulative survival, you would multiply this value by the value above it. So that's 1 times 0.98, you end up with 0.98. And you can calculate the cumulative survival for actually mortality by 1 minus the cumulative survival. So 2% had died at day 34. Go to the next longest follow-up period, which was 35 days. At that point, there were 49 people at risk because one person had died. But then another person died on day 35. So you calculate the probability of surviving. That's 48 divided by 49, because 49 were at risk, one died, 48 left living. That's 0.976. Multiply that by 0.98, and you come up with a value of 0.96. Go to day 44, and there are 48 people at risk because 2 had died. Another person died. 47 divided by 48, and then you calculate this new risk, cumulative risk of 0.94. Now we go to day 57. There were 47 people at risk at this point because 3 had already died, but we had now 1 loss to follow-up. On that particular day, nobody died, so survival is 47 out of 47 or 100%. And when you multiply that for 9.4, the survival probability doesn't change when somebody is censored. And so it's important to note, if you drop out, it doesn't change the probability of survival, it just changes the number at risk. So in day 75, we have 46 people at risk because 3 had died and 1 was lost to follow-up, and you go on and on until you calculate the rest. And then these are plotted on the graph here with each step representing 1 or more events happening. I would guess at this point, there were probably 2 people left, and 1 person had the event, and that maybe 3 people, but you can see this is proportional to the amount of people to sample size. If you have 2 left and 1 has the event, this is going to drop 50% of what is the remaining height of the survival curve from 0. So, and the orange squares are the censored values. And looking at this, if you want to see if we have kind of random censoring, that's good. Looks like it's pretty constant across the curve. So if you look at a little bit simplified curve here, each drop is 1 or more events in the Kaplan curve. And these, now you're using hairs rather than dots. These are indicating where censored values are. And you see this, somebody is censored, but the survivor function does not change, only when somebody actually has the event. And you can use this where you know that if you have a large sample size, you're going to have a smoother, this is from the empirical data, it's still going to be rough because you're still going to have places where you have the curve is dropping. It's kind of like somebody with a shaky hand trying to draw a straight line. But if you have a small sample size, you're going to see, especially like if you're doing a lot of basic science research where you have small sample sizes, like maybe 10 animals in a group, you're going to see a lot more stepped graph. And this is important because you can look at it and you know that if you want to judge the quality of a study, you know studies have larger sample sizes. They're often better estimates of what's happening, and you might want to judge the results that way. You can calculate your milestones from a single Kaplan-Meier or how many Kaplan-Meier curves you have in your graph by going from the median here, 50% survival, going over to the curve and dropping down. So median survival is about 3.2 years. At 5% survival, or sorry, 5 years survival, you can go up to the curve and across and see 5-year survival is about 28%. And you can also, or a longer curve, this one has been mathematically smoothed a bit, but you can have a 1-year survival, calculate that 5-year and 10-year survival. And this can give you an idea of how aggressive your disease is. And comparing 2 curves, sorry, this is a little messy. I was trying to make it look a bit better. But if you want to, here's a graph looking at survival after surgery for lung cancer. And you have the graph where you want to be the blue line, which is women, because they tend to have better survival over time. You can look at median survival and say the difference in median survival between men and women is about 2 years. And the difference at 5-year survival is about 8% more in women. So even without any kind of stats, you can come up with some nice description about what's happening with your disease process. So you can use Kaplan-Meier's to do that, just to describe curves that you can look at for median survival in different times. But then if you want to apply statistical tests, you can do a log rank test. I include Wilcoxon test here because PRISM includes both, and I want to outline the differences, but I'm going to tell you to, unless there's a very good reason, to use the log rank tests over the Wilcoxon. And if you have more complex data or you have other variables that you want to include in your analysis, you can certainly stratify your Kaplan-Meier curves to look at differences by time or by maybe like sex and such. But if you have more complex data, you are going to want to do a Cox proportional hazards regression model, and also where you can calculate hazard ratio, what gives you an overall measure of effect of how big the difference is, like you're at twice the risk or half the risk for experiencing the event. So the log rank test for comparing curves, it doesn't weight, it goes through the entire length of the survival curve, and it weighs all the time points the same. And it is a standard, and it should be your first choice of doing a survival analysis. The Gahan-Breslow-Wilcoxon, which I'll just call Wilcoxon, is the test that PRISM offers. What it does is it weights the data earlier on in the curve. It weights when you have the larger sample size. So as it will look more at the data, will weight it at earlier time points rather than later. And it's more powerful at detecting if there's an early change at the beginning of the time course than the log rank is, which takes a whole curve into account. But the results can be misleading if you have a lot of early censoring. And also I would not use it if you have small sample sizes, which would kind of preclude it from a lot of basic science experiments using animals, for example. Now, for our examples from Nature, here's a paper published looking at EGFR mutation in non-small cell lung cancer. And what they did is they stratified these EGFR mutations into classical and atypical. And here is don't ask me how they did that. If you're interested, please read the paper. But here is from their figure 1, they have panel D has a survival graph in 264 people with classical mutations and 109 with atypical. And you can see that you would rather have classical because the atypical actually has worse survival than the classical. They provide here's the median time they use to treatment failure as their event. And it was 16 months in the classical. So you can go out here, and I guess it's about here, and drop it down, looks right, and 9 months for the atypical mutations. Now, they didn't include in here any kind of a p-value or any kind of measurement, but they did include it in the text where they calculated a hazard ratio with its p-value associated with that. So this hazard ratio is saying that people who are atypical are 80% more likely to experience or to die as compared overall to those with the classical mutations. So how would we plot this data? Because Nature is very nice in that in recent years, they are requiring or asking authors to make their data available to readers, and some will provide it with the manuscript, and it will be available on the Nature website, and some will say, ask the authors, they'll give it to you for good reason. But this paper had the results, and here is just a classical way that you would, this is a truncated, this is actually the lower part of the Excel table, but they include their key for what is censored and what is event. But here they have 7 months, this person was censored, 23 months, this person was had the event, and which was died. And this is for the classical group and the atypical group here. And they didn't have to sort it in order from shortest to longest. So that the program will do that for you. So you just would copy that into Prism. But I just wanted to take a little short step here and look at the probability of are the assumptions met. I plotted it out. Here's the curve, and you could see that they don't cross. So probably we can assume that the risks are fairly constant. We don't have to, there's kind of like a proportionality to the relationship of the survival curve. So I think that's probably okay. But I'm a little bit worried about the censoring between the two groups. One, this looks like a pretty constant and random pattern over most of the early part where most of the sample size is. As we get into smaller samples, it gets a little bit less certain, but I'm not that worried about that. I think it's better here where we have the larger sample size. But with the atypical curve, we see that there is not a kind of random over, and it tends to be clumped. I would worry about that if I plotted this data, and I would want to explore and maybe find an explanation and say, well, I don't think this is going to bias my estimate with the survival curve, or maybe it will. Another warning sign is that only 10% of the atypical ones were censored, whereas 50% of the classical were. So again, I would wonder about that. And I didn't read the paper all the way to see if they addressed this issue or if they even thought about it. But we're going to go on and assume this does not bias, and we're just going to go ahead with the analysis and everything is okay. So you open Prism, and when you open Prism, you get that nice window, and you can select what kind of data you're putting in and what kind of analysis. XY is going to have you do like linear regression, and also you can do correlation and such. But we are doing survival. So we pick survival, and we're going to enter data. So we go ahead and hit create. And we come to, it opens up where you do the data table, and I just copied and pasted Control-C, Control-V, and copied the data over. Prism inserted all these decimal places. I could change that, but no, I don't need to. That's all right. It can be 7.0000 days if you want. And I always, this is good practice if you're doing Prism, is label the data table when you put the data in. This is the Robichaud figure 1D. So this carries them through the results, and you know where the graphs and results, if you're going to be adding other figures or other analyses to it, this will help keep it straight. So you've got the data in, and you go then, you hit the analyze button, and this pops up, and it will automatically highlight survival because you asked to put it in a survival format, and it automatically highlights the two groups that you have entered data into. If you wanted to just do one graph, you could just uncheck one of the boxes and you can plot the curve for that particular graph, but we want both, so hit OK. You get another box that asks you about the parameters for your survival curve. And this is the default. It's assuming that you categorized your event as 1 and your censored subject as 0, but you could change that to 99 and 23 if you wanted. You can do it any way you want, but I think it's easier to keep it straight if you do it as a 1 and 0. It automatically also highlights both tests. It gives you the Wilcoxon and log rank. I kept that because I wanted to show you the differences between the two. You can do the table probability. You can either do percent, or other one would be the proportion, which would be 0 to 1, and this is from 0 to 100%. I didn't do any error bars on this for this example, but I'm going to also show the censored subjects on graph, and I kept these at 4 decimal points and such to the 4. So here are the results. You get 3 tabs in the results section for the particular survival data. It gives you the log rank, the Wilcoxon. It calculates median survival for you precisely. And it also gives you a hazard ratio. This is not adjusted by any other comorbidities, but it says this is the hazard ratio if you're comparing classical to atypical, because classical was entered into the A column and atypical in the B column. So it's saying that the classical is at reduced risk, about half the risk according to the B column for death. And this is doing atypical to classical, so the reverse of that, where they're at double the risk. So the Wilcoxon test, we have a P of less than 0.0001. You have the same result for the Wilcoxon. So you come to the same conclusion if you used either test, but notice that the test statistic is slightly larger for the Wilcoxon compared to the chi-square. And that's because in the earlier part of the curve that the Wilcoxon weights, there's a early and a wide separation from the very beginning of the curve. So this kind of biases, and that this would give you, could be potentially a problem. Say that you want to p-hack and you run your data, you run both tests, and you give you the one that gives you the p value that you like. Do not do that. Do not shop by doing that. Decide you're going to use a log rank and use that, even if this turns out to be not significant and this is. Only use a Wilcoxon if you have a very specific reason to use it. Okay, I'm going to have to hurry because I've only got 14 minutes left. Here are the other tabs. This also gives you the median survival and would give you the number of censored subjects. If you have also any possible data, say like negative values, that can point it out. But also if you ask for the analysis, it will sometimes point out that you have data that don't really match. And here you have the number at risk. So you can start if you want to do a table that does the number at risk at each time point. So at 0 time point, you have 264 and 109. If you want to go to like 2 months, it's 256 and 95. So you can use that if the paper you're publishing in requires you to have such a table. Now for graphing it, I just decided I'm going to use the hairs on it because that's what they used in the graph for the paper. Here's if you wanted to do the circles, you can use that for the empirical data. If you want a more smoothed curve, you can use that, but we're going to use empirical data for that. We're keeping it the percentages and not using the fractions. So from 0 to 100%, we're plotting censored points only. I don't think it's really necessary to do all points, which includes events. I think that can get confusing. And I'm not doing any error bars in this example. And here's the result. I did modify it. I modified the Y and the X axis. And I highlighted the censored values for green for the classical and black on the red curve for atypical. And what you would report with this, you would report, p log rank p value less than 0.0001 and probably put that in your curve or in your figure at that point, and maybe include median values as well. And here is if you wanted to put that table underneath it, you can go through this table and find the numbers that meet the time points that were on the graph and give the idea of what people are at risk at each time period. If you want to calculate some 95 or error bars around your curve, because what we're doing is we're doing a sample of people with atypical EGFR, not the whole world of people with atypical EGFR and non-small cell lung cancer. So because we're doing by sample, we know this is an estimate of the truth. And you can calculate, and you'll see some curves, some survival curves will have like they usually do a colored band around that, or you can do these dotted lines that just give an idea that we think the truth probably will lie somewhere between these lines, given that we have some error in our measurement in our sample that could differ from the final example. And you do that by going in and you can color code the error bars and the thickness and the type of line that you want to do. The next paper, which I'll go over quickly, is looking at, it was elevated NSD3 histone methylation activity in squamous cell lung cancer. I just happened to choose lung cancer, not for any particular reason. They just had nice survival curves to study. And here they were looking at the deletion, different deletions of this and how this affected survival. And they had 10 mice and 8 mice and 10 mice in the 3 groups. And here is the data from this. Now, what I noticed right away when I looked at this curve, I assumed that all these marks were censored values, because usually that's what you show. But what they show here is actually there were no censored values. Every mouse died. The survival curve actually went to 0 because every mouse died, but at different time points in this graph. So I think what they did is they plotted all points, but I think it would have been better if they didn't. So you capture the data you copy it into Prism here, and I renamed it to the author's name and the figure 1F. I went to analyze, chose survival curve, and we have the 3 different, it chooses the 3 groups. So yes, we'll plot them all on that. And it comes up with it gives you the censored is 0 and the event is 1. It gives you a different selection of tests. It still gives you the log rank and the Wilcoxon because you're comparing 3 or more groups, but it also gives you a test for trend. And that's if you have the data that, if say you're looking at low grade, mid grade, or high grade cancer, you would expect survival to vary, and that people with low grade probably have better survival and people with high grade have lower survival. And if you put your data in that order in your the data in the table, then you could ask for a test for trend, and that will tell you if like survival is worse from low grade to middle grade, from middle grade to high grade, and we'll give you a test statistic for that. This is meaningless because there was really no order for these. And so this is not really anything you should pay attention to. I just included it for the example. Here it gives the log rank and for the Wilcoxon test. You see the p-values are a little different. In this case, the test statistics are a little smaller for the Wilcoxon compared to the chi-square, to the log rank, because it's weighting it to the earlier time periods, and it's just not as accurate. It's not as sensitive to the fact that you get late separation of the curves. So in this case, the Wilcoxon test would not really be appropriate, but I would advise anyway to really use the log rank test. And I think what they did was, when they plotted this, was they plot symbols at all points, and that's how they got all the dots at their everywhere. But I think they really needed to say plot censored, and there were no censored, so you had no dots on there. Now they calculated p-values, and I want to make one point about p-values, that it's not necessary to go to 4 decimal places on every p-value you report. Reporting 0.42 is perfectly fine, and you should probably think to report 2 would be fine. It doesn't matter that it's 4249. 42 is enough because it doesn't cross that threshold of significance that you set, and usually that's at 0.05. And this I would report as 0.003. This one I can leave at 0.0002. But the idea is, quoting extra decimal places of significance doesn't really mean that much. And as a standard, I would stick to 2, or in this case to 3. And I think why you so often, because so many people use GraphPad Prism for their graphics, the reason you so often see 4 decimal points is because that's the default in Prism. But please be aware of that. But what they did was that Prism doesn't offer a multiple comparisons test that would adjust for multiple comparison issues. What you do, if you find that you get that p of, it was 0.0006 of the log rank, you can go back and say, I want to know where the difference lies. And you can go and do a 2x2 comparison between the curves. And these are the p-values. When I did that, I compared like A to B, A to C, and B to C. Here's the 0.002002, and here's the 4249 and the 0028. And they didn't adjust for multiple comparisons, which may or may not be an issue, but something that you should discuss. So my summary for this now is, if you have time to event, if you want to know the time of when something happens, that you are doing a longitudinal study, survival analysis is the analysis for you. It uses censoring to help you allow for the fact that you're going to lose people, and you have people with incomplete follow-up. The Kaplan-Meier method is the most popular. It's really intuitive and it's easy to do. And you can use it to determine important time points like median survival or 5-year survival. And the log rank test will allow you to do comparisons between the survival curves to give you that little bit of statistical evidence to help you determine if there is a difference between your groups. But it is only a test of significance and not an estimate of the true size of the difference between the groups. So even if you get a really small p-value, that doesn't mean that it's a really big difference or a very really important difference. It just could be you have a big sample size and your p-value is smaller because of that. So if you do want an estimate, other than maybe comparing the differences between median survival or difference at 5-year survival between curves, and you have different comorbidities you might want to take into account, or different things like age or maybe sex that you want to, because risk would differ by sex and you want to manage that in your model and refine your estimate, then you would want to do something more like a Cox proportional hazards model, which would be for a future lecture. And so if you want any data from the examples I had to practice, please email me and I will send it to you. Any questions? I have 4 minutes.
Hey, Kathleen.
Hi.
So this very nice presentation and really great examples. Given that I'm sure many of us probably didn't memorize exactly all the steps that you did. Would you be open to sharing the slides? And then
Yes, I think they're posting the video
Okay.
too, but I can certainly, if Andrew, can I give you the slide set to post? And maybe I can
yeah,
post.
I'm not sure if we can, I'm not sure we would post it, but yeah, if people either reach out to me, you, or Andrew,
Yeah.
we can share that.
Okay, or Jim, if you want me to send you the slide set, I can email it to you too.
that would be great. And then you have your email here, so if people have questions, they can just contact you directly, or
Sure.
just contact Andrew. Okay.
Sure, I'm happy to help you with any things, particularly with Prism. If you've got some issues.
Great. Any other questions from the audience?
I have one, Kathleen. So a lot of the studies that I see, at least related to this question, we'll have a publicly available cancer set, and then we'll have a gene of interest, and we'll go back and regroup those patients based on mutated or not, or high or low, whatever it is. I'm thinking based on the number of covariates that can be impacting survival, a log rank test is probably rarely appropriate there. Or, I wanted to get your thoughts on that. Like after you stratify an old data set, what steps would you do, going forward?
Well, you do have, you're worried about multiple comparisons issues if you're doing a bunch of different 2x2 comparisons.
Not multiple comparisons, but different covariates like age, sex, tumor stage, tumor grade, from the beginning.
I mean, how would you handle that with the Kaplan-Meier? I'm not quite sure if I understand the question.
Yeah, so to do a proper analysis, I think you basically hinted at you would need to do a Cox proportional hazard.
Yeah, if you have a large number of covariates that you just want to account for in your model, I would certainly do, because you're going to have some main thing of interest that you're studying, but you're worried that differences by age or gender, or if they're obese or not, certainly you would want to do the multivariate model. You do a Cox proportional. That doesn't mean you couldn't plot Kaplan-Meiers to say, okay, well, we want to look at this gene, whether they have it or not. And you could look at that. You could adjust your analyses if you wanted to match, for example, like they did with that one study with COVID, where they matched the males and females to try to see if there was a true difference between males and females. They matched females with the same propensity scores for different comorbidities, so that they had a way of trying to control for that. But you have to have a rather large sample size in order to be able to do that. So yeah, for the most part, if you are looking at a number of different covariates, I would suggest doing a Cox proportional hazards model.
Okay.
Dr. Torkko, this is Xiao Wei. I'm a coming T32 research fellow at Palliative Care and Aging at General Internal Medicine Division. And this may be a little off kind of topic question. You studied a lot of examples about related to advanced lung cancer and non-small cell lung cancer. Is it because you see a lot of kind of activities, research activities, all the way from basic science to the applicational population-based clinical trials? Do you have any comments on the research frontier specifically related to biostats in this area that leads to, what's your estimation about the breakthrough of some new medications coming through in this area for lung cancer?
Well, that's a deep question. I don't think
Thank
I'm
you.
really qualified to answer that. But certainly with the examples that I chose for this study was I just did a search on the Nature website, and I was looking for examples of nice looking survival curves that had data. And maybe what I found out is that people who study lung cancer are more likely to provide data than people who maybe study other types of cancer and publish in Nature. So I don't think I really can't answer without a bunch of deep thought and research your specific question, but I wouldn't put a lot of weight on the examples that I chose. I think it was just a happy accident that I happened to have lung cancer examples. Now, I did go out and look for COVID ones because I thought that was a timely kind of topic to discuss for this.
Yeah, the coincidence leads to a lot of new discoveries and coincidence that may kind of all conspire to some new innovations, I guess.
It could. Maybe we've discovered something important today. We'll have to see.
Thank you.
Okay.
Okay, I think we're a little bit over unless anyone else has a quick question.
And if you do, you please email me. I'm happy to email and chat. It's kind of lonely in Sydney here in my office.
Okay, well, thank you very much again
Okay.
for giving the talk, Kathleen. That was very good.
Okay, thank you. So, bye.